Hello and welcome to part 3 of the PFAS identification series. This was a series more focused on the analytical chemistry of PFAS. If you're looking for more basic information, you can check out the series I did on PFAS background. But this is part 3. Parts 1 and 2 were about isotope ratios and mass defect. Now part 3 today is going to be about extraction, so how you get PFAS out of an environmental sample and into a sample that you can analyze on an instrument. So to get started, PFAS sample preparation, getting a clean sample. So why is sample preparation important? So sample preparation does three things. First, it dissolves your compounds in a solvent that you can then go on to analyze on instrumentation. It concentrates your compounds, so it takes something that might be at very small levels, like parts per trillion in the environment, and concentrates it up to parts per billion or parts per million, something that you can look at on an instrument and be able to see and know the concentration. And then third would be removing contaminants. So any sample has contaminants in it that might interfere with your instrumental assay. So these are kind of the points of sample preparation. Practically, what does this look like? Though there's a few different ways to get PFAS out of a solution. So nonpolar interactions would be the number one way. PFAS in general are nonpolar. All those CF bonds, all those fluorines covering the carbons, really make it not like water, and it can dissolve a little better in solvents. Although with the charged end that you normally see on them, like our PFOSphorus rhinoceros horn here, which is negatively charged, that will interact a lot with things like water and methanol that are protic that can do hydrogen bonding. I threw up a picture here. This is a fatty acid. This is I'm not good with my fatty acids, but this is octanoate. I don't remember the name of the fatty acid, but this is in coconut oil. And it's a very common one. And you can see it's similar structure. We have a long chain and then a charged head group. So what happens is if you have a protic solvent, especially like methanol, you get these nonpolar interactions, and you can see methanol might have nonpolar and polar interactions. So you get with that CH3 group on methanol, you would get interactions with the fluorocarbon chain, and with that OH head group, you'd get interactions with the head group of the PFAS or the PFAS. So this is a way to get PFAS into solution because they have a good strong affinity for things like methanol, and they get completely solvated. So in a soil or a solid sample that's contaminated with PFAS, you see our PFOSphorus here in our soil. Usually what happens is you take a big soil sample and you subsample it, usually 0.5 gram to 1 gram, and then you add something like methanol, 5 to 10 mils, and you can see there when we added the methanol, that's going to pull our PFAS out of the soil and into that solution. So we do this, and it's quantitative, so you can back calculate if there's that much in our 10 mils of methanol, how much is there in our soil sample. And this is the basis of solid sampling. It's very simple, right? We're taking soils and adding methanol, and that's it, and we're just analyzing the methanol. With water samples and with other kind of aqueous PFAS solutions, it becomes a little more complicated. Methanol mixes just fine with water, so if we add it to water, all we've done is dilute it. So when we have something like PFAS in water, we can use 3 different mechanisms, and there's different methods that use these or require these. The first one is pretty cool. It's ion exchange. So with ion exchange, we're using the affinity of a sorbent in a tube, almost like a filter. This tube would have a positive charge under some conditions, which would attract the negative charge of our PFAS, and here of our PFOSphorus. And that's a pretty strong attachment there. And then you can rinse all the junk through while the PFOS or PFAS are bound to the filter. So that's handy. And then you can add a different kind of buffer or something to neutralize those positives. And then, of course, our PFAS, any acidic PFAS that is, such as PFOS, will come off of the tube, and you can collect it for further analysis. So this is a good way to clean up, because you would hope that a lot of your junk that's in the samples is not acidic and would just flow right through. So the other way, this is kind of the older way to do PFAS cleanup, is the way that method 537 would have done. And this is with just reverse phase. So similar to methanol, you use the fluorocarbon group on the PFAS molecule just to stick, It's sticky to certain things, so you would use C18 or divinylbenzene, something like that. Something that's also nonpolar, like attracts like. We put the PFAS on there and they stick. This is good, but for some more polar PFAS, it's actually not good. It's not enough. It's not enough attraction to really hold them. And so we wash the PFAS off using something that's even more polar like methanol, and it'll pull off the tube. The final way to do sample cleanup is to just have your PFAS already in a solution with methanol, such as like from a soil extract, and pass it straight through what we call a normal phase tube. What we use for PFAS is actually extremely simple. It's carbon, so it's pretty much charcoal. We run it through a charcoal filter, and if PFAS is dissolved, if they're dissolved in methanol, they'll go straight through there, but kind of stuff that's in the sample from the environment or serum or something like that would stick to the carbon, whereas the PFAS would pass right through. If you have the PFAS in water, the carbon would act like a reverse phase, so you could use that either way. So with drinking water samples, a typical sample prep, and if drinking water is unique because it has a very specific regulation, EPA 533 and 537.1 are the two regulations covering drinking water. So if you are analyzing drinking water and you need your data to be official, you have to follow those methods. So what you do, you take a full 250 mils, so a full bottle of water, and you can see our PFAS in there. You pass it through, and when you pass it through that tube, it could be ion exchange or reverse phase, depending on the method. The PFAS are stuck to the tube, and then we rinse through all the other nasty stuff. And then we take something like methanol, rinse the sample bottle. You always want to rinse the sample bottle because we would have some PFAS. I should have put it in the animation, but you'd have some still stuck in there, stuck to the bottle. So you're using that methanol to rinse it out and then passing the methanol through the tube. That collects all of our PFAS into a solution. And only one more step and we can do the analysis. That step, also required by these methods, is to use air or nitrogen to evaporate that sample down to about 1 mil. And so we've gone from 250 mils, the same amount of PFAS, all the way concentrated down into 1 mil. So we've taken something that might be parts per trillion and we've made it close to parts per billion. It makes it much easier to analyze because it's concentrated. So that's how we do drinking water. That 250 to 1 concentration factor is important to remember because that means if you were to run that final sample on any instrumentation, whatever value you get, you need to divide by 250 because you have concentrated it by 250. You've already multiplied your sample by 250, so you want to divide your answer to get back to what the original number was. The example here shows 5 of our PFOS in 250 mils, going from 5 PFOS in 1 mil. So we started out with 0.02 per mil, so that's 5 over 250. We ended up with 5 per mil, so that's our 250 to 1 concentration factor. So important considerations, I mentioned this a minute ago, but PFAS stick to plastic and glass. That's why we rinse the container with that methanol. This is important to know in any transfer step, whether it's pipetting or transferring to graduated cylinders. Know that they've stuck to that plastic and glass and you need methanol to rinse them off. Another thing that happens with PFAS is they aggregate at surfaces, especially of water, where those fluorocarbon tails, they hate water so much they'll actually stick out of the water and their more polar heads will stick in, so they're kind of like doing little handstands. So anytime you subsample or anytime you sample something, you want to make sure it's properly mixed. So you want to shake or vortex any containers before pulling out a sample. So that's all for today for sample preparation. That was a very simplified version, but I just wanted to give you the basic description. Solid samples, it's kind of a shake with solvent, pull off the solvent. You can clean it up or you can analyze it straight. But with water, we can also just do dilute and shoot, or we can do sample preparation like I just showed, where you do that solid phase extraction. There's methods online. There's products sold specifically for this. You can check that out. Okay, thank you for joining. That is PFAS extraction, very much simplified. The next episode will be about internal standards. So we will talk about internal standards next. Thanks for joining, and be sure to like and subscribe. Like any good YouTuber, I need to ask for that. Thank you.